Lesson 2, Summation Notation. Writing area as a limit. Summation notation, or sigma notation, gives us a compact way to write Riemann sums into a single expression. This lesson will lay the foundation for the definition of the definite integral. While you may have seen sigma notation in an earlier course, we will focus on using this tool to write Riemann sums. So, summation notation is a method for summing up a finite number of terms in a sequence. And where the Greek letter sigma is the operator that indicates this process. So when you see sigma, you should know that, oh, I'm going to start adding things. And what am I going to add? Well, I'm going to add whatever this thing is, right? And how many times am I going to add it? Well, I'm going to add it from k equals 1 to n. So that's what we look at it as. So now, for this one, and they give you all the names of them, you know, of the different spots there. You've got your summation sign and the index of summation, k equals 1, and then the upper limit to n. So that's how you read it, k equals 1 to n, and then you've got your expression, x sub k. And so for this, you know, main one, this would be like x sub 1 plus x sub 2 plus x sub 3 plus dot, 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 plus x sub n. Then you would be done because n is your last one. That's your stopping point. And there's plus signs in between because that's what sigma means. So for example number 1, we're going to go from k equals 1 to 4, and we're going to use 3k minus 2. So 3 times, and we're going to put our first k in. That is our k equals 1 minus 2 plus 3 times k equals 2 minus 2 plus 3 times k equals 3 minus 2 plus 3 times k equals 4 minus 2. And 4 was your last one. That's where you stopped. So this is going to be 3 minus 2 plus 6 minus 2 plus 9 minus 2 plus 12 minus 2. So 1 plus 4 plus 7 plus 10. You should get 22. Okay, so that is your sigma for that example number 1. Example number 2, consider the sum 9 plus 25 plus 49 plus 81. Choose all the answers that apply. So what they want you to do is figure out, because it might be more than one, whether this summation will give you 9 plus 25 plus 49 plus 81. So if I put a 1 in here, I would get 1 plus 1 is 2 plus 7 is 9. So for my first one, I would get a 9. If I put a 2 in, I would get 4 plus 6 plus 7 is 13. So since I would get 13 on that second one, I already know that I'm not going to get it. Plus, there's only going to be 3 of them because I'm only going from n equals 1 to 3. So I knew right away there were only going to be 3 numbers because if I, you know, once I put that 3 in, I'd get 9, 12, I'd get 19. So that definitely does not equal the 9 plus 25 plus 49 plus 81. So we don't want to circle that A. Now let's try B. Our first one is 0. So if I put a 0 in for n and then I am left with 3 squared, I would get 9 for the first one. Plus. And if I put a 1 in, because when I go from 0 to 3, that means I start at 0 and then I go to 1, 2, and 3. So 1 is next. So 2 times 1 is 2 plus 3 is 5 squared is 25. Plus. And then I put a 2 in. 2 times 2 is 4 plus 3 is 7 squared is 49. Then I lastly put a 3 in. 2 times 3 is 6 plus 3 is 9 squared is 81. So this one I would circle as a yes. That one does equal what they wanted us. Now we need to try C. We're going from 1 to 4. So I put a 1 in. I get 2 times 1 is 2 plus 1 is 3 squared is 9. Then I put a 2 in. 2 times 2 is 4, plus 1 is 5, squared is 25. Then I put a 3 in. 2 times 3 is 6, plus 1 is 7, squared is 49. Plus, then I put a 4 in. 2 times 4 is 8, plus 1 is 9, squared is 81. So this one also works. Now let's do D. I put a 1 in. 2 times 1 is 2, minus 1 is 1, squared is 1. So we already know that D is not going to be one of them because the first number is not the same. So that one, B and C, both equaled that sum. It is acceptable to use any letter for the index of summation. Most textbooks will use I, K, or N. Be aware that some summation expressions may have other variables. For example, summation K equals 1 to 4 of 2 to the K times X to the 2K minus 1. So for that one, you're only putting in the 1 for K. So you end up with 2x plus 4x cubed plus 8x to the 5th plus 16x to the 7th. So only put your numbers into the variable that is on the index. If there is another variable there, you just leave it alone. And you know, it's part of your summation. This will help you understand how summation notation can represent Riemann sums for a function. So for summation I equals 1 to 4, f of x, and they've got like a star on that, f of x star sub I. Gosh, that's a mouthful. But that x star is just some arbitrary x on any interval. You know, any like interval AB. And so you're basically, notice that this is like, if we said from 1 to 4, then, you know, that would be your f of x of 1, you know, or f of 1 plus f of 2 plus f of 3 plus f of 4. So, you know, if my x's were from 1 to 4. So these are going to be arbitrary x values depending on what the situation is, okay? So now, writing a Riemann sum in summation notation. Example number 3. For the function y equals the square root of x, draw rectangles forming a right-hand sum with 6 equal subdivisions, n equals 6, on the interval. And notice this is our closed interval AB, so our A is 1 and our B is 4. Our closed interval is 1, 4, where the width of each rectangle is delta x equals b minus a over n. So in the last lesson that we did, we also talked about b minus a over n. So I've got 4 minus 1 over 6. So 4 minus 1 is 3. 3/6 is 1/2. That means each one of our intervals is going to be a half. And look how this x-axis is drawn. And we start at 1, so I'm going to just, you know, show my divisions here because it's going to be every single half from 1 to 4, and there should be 6 of them when you're done. So 1, 2, 3, 4, 5, 6. Sorry, 1, 2, 3, 4, 5, 6. So there are 6 of those. And now what we're going to do is we're going to use right-hand sum. So that means for this first one here, here's my left point on the function, here's my right point on the function. Right-hand sum takes the right one over, and then that is the area that we're going to use as an estimate for the area under the curve. Right-hand sum, I go to the right, and then I go over and down to declare what my rectangle looks like, and that's the area I'm going to use, or I'm going to use for calculating. So right hand go over and down, and that's my area. Right hand go over and down, that's my area. Right hand go over and down, that's my area. And then the last one, right hand go over and down, that's my area. Notice, on a right hand Riemann sum, you don't end up using your value at 1 at all, right? Because it's a right hand Riemann sum. So this value at 1 right here that I'm pointing to, and you can't see, this won't be used at all because that's the left hand side. But the very last one will be used. On a left hand Riemann sum, if we would have been doing left, your first one is used, but your last one isn't. So that's just kind of a pattern that you'll notice once you're starting to do these LRAM and RRAM type problems. So our goal is to find a general expression for the area of the kth rectangle A sub k. Well, I have not finished this part A yet. What I would like to do is show you what this RRAM is going to look like. So if I was going to do RRAM here, and I would do like sub 6 because I've got 6 rectangles, each one of the rectangles is a half wide, right? Every single one of these is a half wide. The width of them is going to be the function's value at that point. So for the first rectangle, I have 1/2 times, and it would be the square root of 3/2, because that's what my right hand is, because this is at 1.5, which is 3/2, right? This one is at 3/2, that one is at 5/2, that one is at 7/2, okay? And then so that's the area of my first rectangle. Plus, and then my second rectangle, it's also a half wide, and it's at 2, so square root of 2, because that's what my function is. Plus, and then my next one is a half wide also, and it's at 5/2, so square root of 5/2. Plus 1/2, and then the next one's at 3, so square root of 3. Plus 1/2, this one is at 7/2, so square root of 7/2. Plus 1/2, and the last one's at square root of 4. Okay? So look, I got 1, 2, 3, 4, 5, 6 rectangles. Basically, the first one, length times width. And then plus the second one, length times width. Plus dot, 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 dot. All the way down to the last one, length times width. Okay? That's how we got our area. This is our approximation for area under the curve. So, and that's what they're saying here. And, you know, we could figure out what this one is. Notice, though, that if you had, if you were able to, if they were all the same width, you can factor that 1/2 out. And then you'd have, you know, your square root of 3/2 plus square root of 2, plus square root of 5/2, plus square root of 3, plus square root of 7/2, and then plus square root of 4. I'll just put 2. Sorry, my pen's being weird here. Okay. And so, I just want you to see how you've got your area 1 plus area 2 plus area 3 plus area 4 plus area 5 plus area 6, and that ends up being your summation from k equals 1 to 6. Okay, so that's why this is connected to the RRAM, MRAM, LRAM, trapezoidal that we did in the last lesson. So now, for part B, the height of each rectangle is the function value at the right endpoint of the rectangle, which is what I showed you, denoted as x sub k equals a plus delta x times k. Find the expression for the height of the kth rectangle. So your x sub k is equal to a times delta x times k, or plus delta x times k. So now your x sub k, your a is 1. Like, look, there's your ab. So we're just putting in 1 for a. Your delta x is 1/2. So there's your x sub k, 1 plus 1/2 k. Next, you're going to write the area of each rectangle is a of k equals the width times the height, or a of k equals delta x times f of x sub k. Well, so here's your a of k equals, if it's delta x times f of x sub k, well, our function is that square root function. So this is going to be the square root of, and what did we just say our x sub k was? 1 plus 1/2 k. So there's our a of k. That's our a of k function. Finally, write the summation notation for this expression above for values of k from 1 to 4. So we've got summation. Now, we want to be careful, because if we were doing them with a width of 1, it would just be from 1 to 4. But we want to end up with 6 rectangles. So we want to say summation k equals 1 to 6, and this would be 1/2 square root of 1 plus 1/2 k, because that's going to give you your 6 rectangles. And if we put that in our calculator, we end up with 4.911. Is it going to be an overestimate or an underestimate? Well, look up here. You've got extra area. You can see that there's extra area. And we talked about how if it's an increasing function, our RAM is an overestimate. So this is going to be an overestimate. Now, I'm going to go to the Desmos calculator on your Chromebook, and you can see how to put in your summation. I did a couple for the Calc BC that are in there, but on Desmos, you're going to hit function, and normally it comes up as trig right here, and you want to go to miscellaneous, and then look down here, there's summation. And you can say, what did we have? From n equals 1 to 6. And then you're going to put in your 1/2. And then arrow over. And then you want square root of 1 plus... oh, and I used n, by the way, or they use n. And then you want 1/2. And then you have to go and put n in, because if I say from n equals 1 to 6, that's going to be n. So do you see how it already calculated it for us? 4.91148838824. That's where I got my approximation over here in our notes for 4.911. Okay? So that's how you would do it on your calculator. The TI-84 has a summation also, but I don't have my 84 with me, so if you Google it, it'll tell you how to do it. Or you can just use your Desmos. A summary of the procedure to write summation notation. So let's think about this. We had to find the width of each rectangle on the interval from A to B, and we did that by taking delta x equals b minus a over n. Because usually they tell you how many rectangles they want you to use. They might say use 5. They might say use 7. They might say use 4. And that's your n. That's the number of rectangles. N is the number of rectangles. Then it'll tell you we want to find the area under the curve from 1 to 7. That would be your a comma b interval. Or from 0 to 3. That would be your a comma b interval. The second thing, find the right endpoint of each rectangle. So your right endpoint, your x sub k, is equal to your first value, your a, which would be on your closed interval AB. That would be whatever that first number is, plus your delta x, which you just calculated, times k. And you would just leave k there. So you just really need that first number and your delta x. Find the area of the kth rectangle. So that's just going to be delta x times f of x sub k. So our function was a square root function, square root of x. So that's why our f of x ended up being the square root. But if your f of x, if the function that we're looking at is y equals x squared, then our f of x is going to be, whatever that x sub k is squared, because that is your function. And we're going to be doing more of these, so it'll make more sense. Right Riemann sum. K values go from 1 to n. So there's your right Riemann sum. K values going from 1 to n. If it's requesting a left Riemann sum, your K values, are going to go from 0 to n minus 1. Okay, and so just be careful whether they want left or right. And you should be able to make sense of that. Okay, so example number 4. Use the procedure above to write the expression that represents the approximation shown below. So if I'm looking at this, I have some function. They haven't told me what. But when I look at it, it looks like I'm going from 1 to 4. So that would be my closed interval from 1 to 4 would be my A and my B. And it also looks like my delta x is 1/2. So, and I've got 1, 2, 3, 4, 5, 6 triangles. So my n is 6. Come on, pen. So my n is 6. And so 4 minus 1 over 6 gave me my delta x. And my delta x then was 3/6. My delta x was 1/2. Okay, so those are all the things I see here so far. And then notice that they are using the right hand. Because look, for each one of these, like this would be my L, this would be my R for that rectangle. So they're using right hand. This would be my L, this would be my R. They're using right hand. There's my L, my R. They're using right hand. So this is a right Riemann sum. So this is an R Ram 6, right? Because they're using the right hand Riemann sum. It's a decreasing function, so it's an underestimate. And I'll erase that just so you can see it better. And so now, what would our x sub k look like? X sub k is going to be our 1 plus 1/2 k. And our delta x times our x sub k is going to be 1/2 times. And then whatever our function is, we'll be putting that into our function. Okay? So if I'm looking here, I'm thinking that C and D look like what we're trying to find. These two aren't in the format that we need, okay? So now, what's the difference between them? Well, one would have been a left hand, and the other one would have been a right hand. Notice that this one right here is if we would have used LRAM. But this one is the one with RRAM. So our answer for this one is going to be C. So this function has to be 2 over x plus 3. Do you see how they put the 1 plus 1/2 k in where the x is in your function? Whenever we did the, square root of x, we put our 1 plus 1/2 k, that x sub k, into where the x is in our function. So they put 1 plus 1/2 k into the x in their function. So therefore, that tells me what this function is, 2 over x plus 3, even though they didn't give it to us. So hopefully that made sense. I like that one because it made you think, going backwards from it instead of you producing it. Okay, a definite integral represents the area under the curve of a function, and a Riemann sum gives us an approximation of that area. That is a huge statement. You need to know that and understand that, because when they ask you to find the area under the curve using RRAM or MRAM or LRAM or a Riemann sum of some sort, that is an approximation. It's going to have an error. If I wanted to find the exact area, so if I wanted to find the exact area under the curve for that function, I would take the integral of 2 over x plus 3 from 1 to 4 with respect to x, so I would have to say dx. So I would be integrating this function from 1 to 4 with respect to x. This is going to give me the exact area under the curve. Okay, from the curve, in between the curve and the x-axis. That's a definite integral. Okay, so we're gonna define a definite integral, in an integral where you've got a function here, and you're going from a to b. That is called a definite integral. When you calculate that, you're going to get a number as an answer because it is the area under the curve. So imagine that we could create an infinite number of partitions, rectangles, in a Riemann sum. The approximation would get closer to the actual area as the subintervals in the Riemann sum increased. We can't take a Riemann sum with infinite rectangles, n equals infinity, in our summation because infinity isn't a real number. However, if R of n represents the right Riemann sum approximation with n subdivisions, we can use limits when we want to take something to infinity. So then the exact value of the definite integral can be shown as the limit as n goes to infinity of that R of n. So if R of n is a right Riemann sum, we said it was b minus a over n because that was our delta x, right? And here's us adding up all of those y values, right? Because we said, like even on the one up here, we said, oh, well, look, I could take my delta x and then make it times the summation of all my y values. That's what they're doing there, and that's what we did right here in this first example. And so delta x times the sum of all the y values. And you have to pick the right y values, don't get me wrong, but it is the sum of those y values. And so if we then wanted to take that and put it into summation notation to find the area under the curve, which is actually going to be equivalent to this definite integral, the integral from a to b f of x dx, we could take this summation of the y value times delta x from k equals 1 to n and take the limit as n goes to infinity. That is the exact value of the definite integral. So this is your Riemann sum definition of the definite integral. Really, really, really important stuff here. Very, very, very important stuff. Put a limit in front of it, take it to infinity, and you've got exact. Okay? And we just use it another way to signify it, that S. You know, this guy right here, it's like an S for summation. So that's kind of cool. That's the integral sign. But think of it like an S for summation, because you're summing up all of those values of, you know, this is like length times width, or, you know, whatever. It doesn't matter which side you call length and which side you call width. But so you're summing up all these length times widths, length times widths. This guy just makes you, instead of using summation, we had to put a limit in front of it. The limit as n goes to infinity of the summation. That's why we use that integration sign, okay? All right, so now the definition of the definite integral. The definite integral of a continuous function f of x over the interval ab, denoted integral from a to b f of x dx, is the limit of a Riemann sum as the number of subdivisions approaches infinity. That is, the area equals the integral from a to b f of x dx equals the limit as n goes to infinity of the summation k equals 1 to n of f of x sub k times delta x. Again, you're just, you know, length times width, length times width. where x sub k is a plus delta x times k, and delta x is b minus a over n. So this sums up the whole thing that we just did, this box right here, okay? So now, example number 5. Write a Riemann sum from a definite integral. Given the graph of the function f of x equals 1/2 x squared plus 1 on the interval from 0 to 4, this exact area can be represented using definite integral notation. So here it is, the integral from 0 to 4, 1/2 x squared plus 1 dx. And it's going to be this shaded region right here. If we found the answer to that, that would be the area under the curve. Write the definite integral as a right Riemann sum with 8 equal subdivisions. Okay, so the first thing I would calculate is my delta x. And so that's going to be my b minus a over, what did they want? 8 subdivisions, okay? So this is going to be 1/2. So my delta x is 1/2. Oh, I know what I wanted to tell you about this. My notes, my thing right here says something different than what my notes say. And I don't remember if your notes say something different here or not. I think your notes might say write the definite integral as the limit of a Riemann sum, not with 8 equal subdivisions. I can't remember. I know I've got myself a little note here in my notes, but I think that that was taken off. So if that's taken off and it's just in, you need to think of this as you've got n number of subdivisions. So this is what your delta x becomes. It becomes 4 over n. Okay, so if they hadn't said with 8 equal subdivisions there, I'm crossing that out because I'm pretty sure that your paper doesn't have the 8 equal subdivisions. I think it wanted you to just write the definite integral as a right Riemann sum. So look at the difference. If they would have said 8, I would have put 8 here, and I would have gotten 1/2. If they don't say 8, they don't tell you. You have to just say there's n number of subdivisions, and then we're going to take n to infinity. So we needed that. Now we need our x sub k. So our x sub k, I'm just doing it over here because I want to write my Riemann sum right here in this spot. But my x sub k is a plus delta x times k. So this is going to be my a is 0, right? Because that's the first in your closed interval, the first number in your closed interval, plus, and then we just decided this was 4 over n times k. So there's your x sub k. Your x sub k is 4k over n. And so now, your f of x sub k, well, your function is 1/2, and then you would put your 4k over n in for the x squared plus 1. Right? That was your function, 1/2 x squared plus 1. So we're putting that x sub k in wherever the x is in your function. So now we can write it as the limit as n goes to infinity, summation k equals 1 to n, 1/2 4k over n squared plus 1, and then times our 4 over n. Because this is giving, come on, pen. This pen does not want to work today. This is your y value. And this is your delta x. right? So that's your, this is like your length times width, your length times width, your length times width. And this is the definite, or this is equivalent to, I should say, this is straight equal sign equivalent to the integral from 0 to 4, 1/2 x squared plus 1 dx. Exactly equal to that. Oops. I'm running out of space there, guys. But those are exactly equal to one another. That is your definite integral written as a right Riemann sum. So I'm hoping that I crossed those out and that's what your paper is. I'm praying that that's, because I thought my notes would make more sense, but they don't. Okay, translating between definite integrals and Riemann sums. Use your calculator to evaluate the definite integral, the integral from 1 to 2, x plus 1 dx. So let's go to Desmos again. And how did I get, oh, there it is. So you had to hit ABC, sorry. There's my function. Here's my integral. And as soon as I hit that, it gives me like, okay, I can put my numbers in now. 1 to 2. And then I'm going to put in, if you want to use just x, it's over there. X plus 1. And then we're going to go back to function. I thought they had a dx there. They have ddx, but they don't just have dx. So let's go to ABC and put dx. Okay. So I'm just learning how to use this Desmos also. But did you notice that once I did that, it gave me 2.5? Okay. And we could actually graph. I can take all this other stuff out of there. And we can actually graph y equals x plus 1. And you're actually looking at the integral from 1 to 2. So the area under the curve from 1 to 2. And so you can see that that's like a trapezoidal area. Let's go back to our notes. We said that that was 2.5 though, right? Okay. And so now find the corresponding Riemann sum for this definite integral. And the width, delta x, would be your, oh, why does this not want to work for me? B minus A over n. So that's going to be 1 over n. And then your x sub k is your A, which is 1, plus your delta x times k. So your x sub k is 1 plus k over n. And then the height is your f of x sub k. So this would just be putting your 1 plus k over n in where the x is here. So 1 plus k over n, that's your x, plus 1, because your function's x plus 1. So if you wanted to add those ones together, you'd get 2 plus k over n. And then part C, write the corresponding Riemann sum. So we've got our limit as n goes to infinity, summation, k equals 1 to n, and then we've got our f of x sub k times delta x. So that would be our corresponding Riemann sum. Evaluate the limit of your Riemann sum on a calculator. What is the answer? And I showed you how to put a summation into your calculator. I'm trying to remember if your calculator does that. I don't know if this one does, but let's look. I know my TI Inspire does allow you to put a limit in, but I don't think this one does. If you know that this is the the integral from 1 to 2x plus 1 dx, it's going to give you the same answer. I don't think that this calculator does it, and I really don't think that your calculator TI-84 does it, but you can do it on my TI Inspire, and when I did that, I got 5/2, which is the same thing as 2.5. So you're just basically, in this example, you're proving that this would be exactly equal to your definite integral. And so on this iPad, I don't have my teacher software for CAS, or I would show it to you. So don't worry about that one. Okay, example number 6. In each of the following problems, translate the definite integral into a Riemann sum. Be sure to check that both forms yield the same numeric values. So what we're going to do here is we're going to look and we're going to see that, okay, well, our integral tells us what our a comma b is, right? Our closed interval. That integral tells us that. I know what my f of x is. My f of x is 3x squared minus 1. And so if my a is 2 and my b is 4, and there's my x sub k, and my delta x is going to be 4 minus 2 over n. So that's going to be 2 over n. Oops. Sorry. Looks like an m now. Then we've got the limit as n goes to infinity, summation, k equals 1 to n. I'm sorry. Yeah, k equals 1 to n. This is going to be 3. Oh, shoot. I forgot to calculate this. So we've got 2 plus 2k over n. So 2 plus 2k over n squared minus 1 times 2 over n. Okay, that would be how you would calculate it. So we calculated our x sub k, our delta x, and we put our values in. And so if they're asking for the value. So from 2 to 4, 3x squared minus 1 dx, you could go back to your Desmos, and we could say the integral from 2 to 4 3x squared minus 1, and then dx, and it gave us 54. Okay, so our value here, 54. And now this next one, our a is -2, our b is 0. A plus delta xk equals my x sub k. My delta x equals 0 minus a minus 2 over n. So 2 over n. So my a is -2 plus 2k over n would be my x sub k. So now, limit as n goes to infinity. Sorry, I know that is all messed up. From k equals 1 to n, this is going to be our negative 2 plus 2k over n plus 3 squared. So look, I put my negative 2 plus 2k over n in for x. And then times 2 over n. If you want to, you could go ahead and simplify, because this would end up being, because I'd add my negative 2 and my 3, that would be 1 plus 2k over n squared times 2 over n. Okay, and then if we put the integral from negative 2 to 0 of x plus 3 squared dx in our calculator, so integral from I guess negative 2, I guess they let you use that, to 3 x plus 3 squared dx. Oh, why did I put negative 2 to 3? Negative 2 to 0. Sorry, guys. Backspace. 0. There we go. So 8.66. This is 8 2/3. Oh my goodness. So 8 2/3, which would be 24, 25, 26 thirds would be your value. I always like to do them as exact decimals. I mean exact fractions. And I usually don't use mixed numbers, but since it gave us 8.66666, we knew that was 2/3, right? And then we could make it that. All right, so now A is 0, B is pi, delta x is pi minus 0 over n, so it's pi over n. Your x sub k is A plus delta x times k. So this is just going to be pi k over n. So we've got our limit as n goes to infinity, summation k equals 1 to n. And this is going to be the sine of pi k n. So I'm putting that x sub k in for x in my function. And then, so that times pi over n. That's your exact, so this and this are exactly equal to one another. This and this are exactly equal to one another. This and this are exactly equal to one another. So if I wanted to find my value of this one from 0 to pi, sine x dx, I'm going to go back to my Desmos, and I'm going to say integral from 0 to pi, which, I don't know where pi is on here. I don't know if you guys do. If you do, then that would be great. Oh, there it is. Never mind. And then we need a function. We need trig. We need sine of x. And then we type in our dx. And it looks like 2. So that one's 2. 2. That's our value. Okay. Example 7. In each of the following, translate the Riemann sum into a definite integral. Check that both forms give the same results. Well, you can't do that because your calculator doesn't do a limit like mine does. So, sorry about that. I mean, you guys can Google it and try and figure out if you can somehow do it, but I think it's only on the CAS for the TI Inspire. But let's try and figure this out. So, my b minus a over n is 5 over n, right? That's my delta x. Okay, so I know that my b minus a is 5. Now, over here, so if this is my x sub k, which I think it is, right? So I think my x sub k is 5k over n minus 2. Negative 2 is my a. Okay? So if b minus a is 5 and my a is negative 2, then b plus 2 equals 5, then b equals 3. So it looks like we've got the integral from negative 2 to 3. And then this looks like 5x minus 1 dx. So, yeah, that's what I want to say it is. From negative 2 to 3, 5x minus 1 dx. And if we calculated that, negative 2 to 3, 5x minus 1 dx, I want you guys to try and put that in your calculator to make sure you know how to use your integral. In the TI-84, it's math 9. If you hit the math button and then number 9, it gives you an integral. And it gives you boxes. It lets you put all this stuff in. And it already has a d there. You have to put the x in, right? So you could put in negative 2 to 3, and then you can put in 5x minus 1, right? And then put your x in, hit enter, and you should get 15 halves. Okay, so let's look at the next one. So my b minus a over n is 2 over n. That's my delta x. And here's my x sub k. So my x sub k, 2k over n minus 2. And so this is my a. So this time, b minus a minus 2 equals 2. So b plus 2 equals 2. So I subtract. So my b is 0. So this seems to be the integral from negative 2 to 0. And then this would be 3x plus 4 dx. So if we put that in to our calculator, and I want you guys to try and do this one. So pause the tape, go to your TI-84, do math 9. If you've got an Inspire, it's going to be the button next to the book. So below the delete, and then to the left of that book. If you hit that, you're going to see definite integral there. And yours is going to go in very similarly. Okay, so for TI Inspire, it's going to be that button. There's a delete button over on the right, and then there's a book, and it's this one right here. It's the one right there next to the book. And when you go there, you can just put everything in. So you should have gotten 2. So again, this is the area under the curve of 3x plus 4 from negative 2 to 0. Okay, and let's do C. So for this one, our b minus a over n is pi over 6n. And so then when I look at my my x sub k here, it looks like my x sub k is k pi over 6n. So that makes me think that my a is 0, right? Because there's no plus anything or minus anything. So if my a is 0, then my b minus 0 over n is pi over 6n. So this is just b over n. So my b is pi over 6. Oops, sorry, 1 over n. Where is it? Okay, there we go. Times 1 over n, sorry. That's what I was trying to do there. Okay, so now I've got the integral from 0 to pi over 6 cosine x dx. Put that in your calculator, please. Make sure you know how to do that. And you should have gotten 1/2. All right, so a Riemann sum in simplified form should be unsimplified before being translated into a definite integral. So, for example, the limit as n goes to infinity of summation k equals 1 to n of k to the third over n to the fourth could be the same thing as the limit as n goes to infinity of summation k equals 1 to n of k over n to the third times 1 over n. That would make more sense because you'd have to have your delta x here. You know, so if you started out with this and you're like, I don't see a delta x, you're going to have to break it out so that you can figure out what your definite integral is. So these are ones that are not broken apart, that you have to actually try and break apart yourself. And so, you know, if we're trying to figure this out, we're thinking limit as n goes to infinity, summation k equals 1 to n. This is what I'm thinking. K over n squared to the 1/2 times 1 over n. So pulling that n out, right? Because basically here you had k over n cubed to the 1/2, right? So you could actually split that up into k over n squared times 1 over n. And so, okay, I'm going to stop right here.